Mr. Sachin Sharma is a certified professional engineer with 13 years of extensive experience in environmental consulting, remediation strategy, project management, and health and safety. He is currently working on a large-scale chromium remediation project in New Jersey. As usual, this will be a 15 to 20-minute presentation followed by a short Q&A session. If anybody has trouble seeing the PowerPoint, please don't hesitate to send me an email. It's Lucie, Lucie, @pureearth.org, and I will try to send you a PDF so that you can follow along. As usual, we're also open to any questions you may have. You can ask them in person at the end, or don't hesitate to put them in the chat, and I will ask them for you. Please go ahead, Sachin.
Hello, everyone. So the goal of today's presentation is to understand about hexavalent chromium, its hazards, and what are the different remediation technologies out there, and how can they be cost effectively used. So with that, my first slide is, generally it covers what topics are we covering on this, and starting with the very basic, the hazards. Most of us would already know what the hazards is, but I wanted to what the hazards are, but I wanted to just put it out there. I had the opportunity to work on one of the very big chrome sites in the past, and you might have seen that movie Erin Brockovich. We were remediating that site, and I think it's still ongoing. The various hazards associated with it is, one of the biggest is the inhalation. If you get chrome dust inhaled, that's the #1 hazard. Rest of them are from the soil or the groundwater. They are there too, but it has a less direct impact on you. The United States Environmental Protection Agency classifies hexchrome in the top 25% of the known human carcinogens. It's more potent than arsenic, benzene, or polychlorinated biphenyls. It's not only toxic to humans, but also to animals and lower life forms, including benthic organisms that live in water near shallow water tables. Chromium exists in generally 3 forms. Hexchrome, we all know. There's a trichrome form, which is less soluble and precipitates out, and then there's a chrome 0, the unrusted chrome form. That's steel gray, solid, used for making steel, and gives that shiny, unrusting capability to steel. The maximum contaminant level for hexchrome in California is 10 micrograms per liter. That's the maximum amount of hexavalent chromium that can be dissolved in water. That's allowed by the government. There are aerosol monitors, basically dust monitors, that can be used to measure concentration of hexavalent chromium in the air if you have a site where excavation or remediation activities are ongoing. It's strongly encouraged to use a good aerosol monitor, something like data RAM model TR1000. Moving on to the next slide. Okay, so this one is about the chromium occurrence and types. So many of us might have already seen chromium impacted waters looking yellowish or greenish kind of color, which is the very first picture on this slide. And so that color could be from a discharge coming from a chrome processing plant or a tannery or electroplating plant, and this color is really based on the pH of the hexavalent chromium. Chromium can exist as dichromate, chromate, and it can have color ranging from orangish to lime greenish, based on the actual pH and the EH of the that actual chromium species in there, based on the complex it's forming. The number 2 photo is actually from a chromium chemical production waste, where a chromium ore is taken, processed, and hexavalent chromium and the trichromium are extracted out of it for industrial uses, and then the residue, which is it has a size ranging from a sand grain to a small pebbles. These stones, basically small stones, they are very rich in hexavalent chromium. They are not a direct hazard until you kind of grind them and inhale the dust. If you just touch the stone, it's okay, it's still a stone, it's not acidic or alkaline. But if it is there, if it is in contact with groundwater, it will slowly start to leach and will impact the groundwater quality. And the dust, that CCPW dust, is very hazardous. Number 3 picture, it's green-gray mud, and green-gray mud is also produced during the chromium waste processing. And this mud is basically lime green dense silt with minor amounts of fine sand and clay. And when this green-gray mud is found in saturated zone, the grain size of the material that has been affected due to weathering process, it can leach chromium for eternity. And this green-gray mud has a high pH. pH is a indicator of the acidity, and the pH for the green-gray mud is from 11 to 12 standard units. And it has very high hexavalent chromium. Number 4 picture is chromium blooms. And well, so this is, some places it's seen, but some places it may not appear. But what happens is, if you have hexavalent chromium in the groundwater, not at the surface, and if there's a rain event and the water table has moved upward, and due to capillary action, the hexchrome particles could be lifted further up, and they can appear on the surface of the ground. And once the precipitation has subsided and it has evaporated, you will still see hexchrome particles in there, and they appear as a greenish, lime greenish color. And that appearance of hexchrome particles and their enrichment on the surface leads to these continuous blooms, these chromium blooms, and that's why this picture number 4 is kind of lime greenish color to it. This can happen where you have shallow water table. This may not happen where you have deeper water table, but many locations, at least in the United States, have shallow water tables, and they have impacts. Okay, so moving on to the next slide. This slide talks about the basic chromium cycle. So let's say we have a discharge from a discharge of hexavalent chromium from an industrial facility, and it goes into the environment. What happens to that hexavalent chromium molecule? It's gonna complex with anything out there, any organics, anion exchange. It's gonna try to geochemically fix itself onto the soil particles. There are some natural oxidants in the environment which will even change the trivalent chromium, which is less hazardous form, into hexavalent chromium, which is the hazardous form of it. One of the oxidant is ultraviolet rays, and the second biggest one is, or actually maybe the first biggest one, is the manganese, because it's so commonly available in the subsurface, let's say 2 feet, 3 feet, 5 feet below ground, where UV cannot penetrate in the soil. You will still have plenty manganese in there that will try to oxidize hexavalent chromium. So this slide basically tells us a very in a generic conceptual sense that what may happen once it goes through. A simple version of this is that hexchrome will try to convert into trichrome, and then trichrome may convert back into hexchrome if it's not permanently geochemically fixed onto something. Okay, so now with that, we come to the different remediation alternatives that we have with the modern technology today. Most of the time, we would like to treat it in situ. If it is not a problem in a river or a stream, if it's just a problem in the groundwater and the soils, and not the surface soils, we would like to treat it in situ because that is the most energy efficient way to treat it. One of the options to treat would be you extract the groundwater, the impacted groundwater, and you mix some chemicals with it that can reduce hexavalent chromium into trivalent chromium. That reduction could be either chemical reduction, that means adding of electrons, or a biological reduction, that you inject something, it ferments, and fermentation makes an electron-rich environment, and then hexavalent chromium accepts those and turns into trivalent chromium. Other option could be you take similar chemicals and mix it in the soil, either through an excavator bucket, or you have big augers that can just move and move the soil with them and mix it. Second option would be your ex-situ option, which, and I know I do say pump and treat here too, but in this pump and treat, you just extract and then you treat your groundwater by filtration methodologies, and then you discharge it to a treatment plant. And then you won't be injecting it back, you would just discharging it somewhere else. That would be pump and treat. And the downside of this technology that your pump and treat time frames, you would need to do extraction for a very long time before each molecule of hexavalent chromium could be targeted. And the second option would be, under ex-situ option, would be soil excavation, that you just excavate the entire impacted area and then send it to a lined landfill, which again is a very costly option and may not be available everywhere in the world. Coming to the third alternative is containment, that if you can't do in situ or ex-situ alternatives, and there's no down gradient receptor that we think will be impacted, then we just insert a sheet pile wall. Sheet pile wall is basically, and I'll be showing you pictures of these too, but it's basically either a metal or a vinyl wall. It's a very big piece of sheet of either metal or vinyl, which is plastic, and we insert that into the ground so that the groundwater cannot go through it, and it just contains it. Second option would be on similar principles, but instead of using plastic or metal, we inject slurry of clay, which has very low permeability, and you inject that and it doesn't let groundwater flow out of that zone where you inject it, and that it just contains everything inside it. And the third option would be a very controlled pump and treat, where you have extraction rate just enough to hydraulically control that area where groundwater is impacted. So you extract just enough so that the impacted groundwater that has hexachrome dissolved in it just doesn't leave your site. It is within the site. You just extract enough. You won't have high extraction rate, and high extraction rate for some site could be, say, 50 gallons per minute or 100 liters per minute. And a low extraction rate could be as low as, half a gallon a minute, or 2 liters per minute. This would be on the lower side of the extraction rate. The last option would be under containment alternative. If you have a surface, if you can do a surface cover, for example, let's say there's a site and you have hexachrome impacted soils on the surface, then you don't want anyone to touch that soil or play in it. You would just put a layer of soil above it, a clean layer of soil. And you can even add some amendments to it that can biologically ferment and change hexavalent chromium to a trivalent chromium state. Okay, so, and please feel free to ask me questions when I'm presenting this, and we can always come back during the, after the presentation as well. Okay, so coming to the next option. Okay, in-situ treatment options. So now discussing about this alternative in-situ treatment, how do we do it? So there are many amendments. We call it amendments. It's or substrates because they rely on certain biological activities to proceed, and this is more suitable for a biological terminology. So biological or organic amendments. There are many out in the market. For example, ethanol, and it's basically beer, ethanol. Or there's lactate, which is also found in the milk, molasses, again coming from the sugar industry, and whey, it comes from milk industry. These all are soluble substrates. They can be injected into the ground or mixed with the soils to create a reducing environment. They ferment, and during the fermentation, they release hydrogen and organic acids, and that creates an oxygen-rich environment, and that turns hexavalent chromium into a trivalent chromium. There are also engineered low solubility substrates in the market, which are very effective, like a polylactate. So you would, because it's a polylactate, you would only need to inject lesser amount of it. Emulsified vegetable oil is one of my favorite ones. It has been heavily used in United States, and it not only treats hexavalent chromium, but many other contaminants out there. For example, trichloroethylene or vinyl chloride and many other chlorinated solvents. It's a very good product. I think the cost for this product is close to like $8 to $9 a gallon, but the longevity, the life of this product is 2 years. Once you inject it, it can continue to have a reducing environment in the subsurface for about 2 years. The next one in the line is the pH buffering. So we can inject some buffers in the ground and change the pH conditions from a high pH where the hexchrome exists to a low pH or alkaline environment, where so acidic environment where where hexchrome can change into trichrome. So this was, so far it was biological reduction, all of these. Now we move on to the chemical reduction. Our goal is to create an electron-rich environment, and so there are chemical reductions out in the market too that can do that. One of my favorite ones is ZVI. It's zero valent iron, and all it is unrusted iron. You can take a scrap metal, and there's a proprietary process. You heat it very high temperature and pressure, and it changes your scrap iron into a zero valent iron, pristine, unrusted form of iron. And you can take that, inject it into the ground, and the rusting, during the rusting process, it'll release electrons that will change your hexavalent chromium to chromium. And if you see the picture that has a ladle in it, and there's a blackish material that's dropping from it, that's your ZVI. And the picture on the top with the two buckets, that's your EVO. ZVI could be nanoscale, it could be micro scale. Based on your the heterogeneity of the soils at the site, you can choose what size particles you want. Many times, for example, in silts and clay, it'll be hard to inject, but in sands where your pore space is between 1 and 5 micrometers or microns, you can easily inject it. And there's a emulsified form of ZVI as well. The next one is calcium polysulfide, a very popular choice among remediation practitioners. What it does is once you inject calcium polysulfide, it releases hydrogen sulfide, H2S, and the sulfide changes to sulfate, and in the process it releases electrons, and those electrons eventually converts hexchrome into trichrome. And the polysulfide means it has many sulfides attached to that calcium molecule. The last one in here is, which we are currently using, is ferroblack, FES. And ferroblack is a complex molecule. FES is just straight, but ferroblack is a it's a tetrahedral shape, and where FES is continuously attached to each other, and it gives a very gives an amorphous form to it, and it's a continuous source of sulfide. And once you put it in the ground, it keeps on providing a slow release of electrons and a very long-lasting, probably the longest lasting reductant on all of these in the list here. It's a very very good chemical reductant. Okay, so this slide basically talks about the bio precipitation.
Sachin?
Yeah.
A quick question, if I may. You give the indication that by doing some reduction and introducing electrons, you will turn the Chrome 6 into a Chrome 3.
Yeah.
The question is, once you remove those reductors, will the Chrome 3 turn back into Chrome 6, meaning that you have to keep having those components inserted and replaced, or once Chrome has turned into 3, it remains Chrome 3?
That's a very good question, Gilles. And most of the times, and this slide actually talks about that. So let's say if we have converted hexchrome, which is a soluble form of it, into trichrome, which is sparingly soluble, and it precipitates out. Once it has precipitated, it geochemically fixes itself to either a soil particle or the other sediments in its neighborhood. And after that, you need very strong acidic conditions to change it into trichrome. The only oxidant is manganese, and manganese, if it's not in the soluble form in direct contact, even if it's in direct contact, you need extreme geochemical conditions to change it. It can be done. For example, let's say you are near an acid mine drainage, which is basically the drainage coming after the mining process, which is very acidic, and you have trichrome in that whole concoction of it, and that'll convert it into hexavalent chromium. But on a site where we injected something, where we modified the geochemistry of it, the likelihood of changing that is next to none. It generally doesn't happen, because once you inject something in the ground, you have changed the geochemistry to an extent that it doesn't happen. And even if there are oxidants present, it needs extreme geochemical condition, like very high pH, very high very low EH, and very low pH and very high EH in order to do that. And that doesn't happen very easily. You need to be in extreme climate to do that. So far, I have not seen any instances where we remediated a site and it converted it back. And that basically because the geochemical fixation of the trichrome is so strong that these reactions won't go back. You can do it in the lab, but in environment, it doesn't happen. I hope I answered your question, Gilles.
Yes, you did. Thank you very much.
Okay, so this slide, let's see. Okay, so this slide basically talks about the bioprecipitation concept, and so it talks about what are the biological reduction processes, and then we also list chemical reductants in there. But what actually happens? Hexchrome changes into trichrome. Trichrome hydrolyzes into a complex, which is and in that complex could be a direct hydroxide of it or an iron hydroxide of it, and that complex is the key that it is stable, and that complex is so heavy that it precipitates out of the solution. That could be your groundwater or your water in the river or your lakes. And that precipitate then geochemically fixes itself. So the first thing what happens, let's say if you do an injection of an organic carbon, which is your amendment or substrate that we have previously called, and as soon as you inject it, it starts to ferment, and it stimulates microbial activity. It's almost like let's say you have milk, and you let it sit, and over after a few days it goes bad and start to stink, and that's the stimulation of the microbial activity. But if you add, let's say, some culture to it, it'll change it to yogurt. It's kind of on those principles. And once that fermentation starts, it creates anaerobic conditions, and anaerobic conditions, all that means is lack of oxygen. And under that environment where there's no oxygen means a reduction environment has started. A reducing environment has started, and that reducing environment is electron rich, and that will convert hexchrome to trichrome. And in the last phase of that is precipitation happens as a complex, and that precipitate fixes itself to the aquifer matrix. Aquifer is just a term used to say groundwater underneath the under your ground surface. Okay, now we come to a case study. This is one of the sites we've been working on, and the picture on the top shows Maurice Canal in 1911. This canal was used to transport chromium related waste and ore around Jersey City, and also used for other industrial purposes. And 100 years later, sometime between between 1911 and 2012, around I think 1950, they stopped doing those operations, and the entire wasteland around the canal was dumped with CCPW waste that consisted of those reddish, whitish, reddish brown stones that we saw earlier, and green gray mud and other CCPW waste. And they raised buildings above that, and 100 years later, when they realized that it is bad, it's really affecting the health of the people, excavation started. And we have excavated about 1 million tons of soils, and there's more ongoing. And the shallow groundwater table was really impacted. All those soils were disposed off-site, and ferroblack was the choice, choice for reductant, because it has very long life, and the operations are still ongoing. And this figure also shows the sheet pile wall that's on the second figure on the bottom, and has an arrow showing the metal sheet pile wall. Those sheet pile wall go, I think, 20 feet below ground, because that's where it meets under layer in order to contain all the impacted groundwater and soil. A very big operation, very big operation. Okay, so and this shows the same site pilot testing, how it was done. So you can see we have this site was all paved with asphalt, and when it was learned that the hexavalent chromium in the groundwater is there, all the operations were shut down. It's industrial area, everything was shut down, and they have to cut through the asphalt and dig up the soil, bring in clean soils, then amend those clean soils with the ferro black, which is ferrous sulfide, and mix it pretty good, and then compact it, and then until the results of clean groundwater quality standards are received, they did not pave, and the site is still not paved. The entire site now, these photos shows just a pilot test, and when it was successful, entire site was excavated, and these operations are still ongoing. Okay, and this slide shows the results. What happened? How much what was the pre-remediation levels and what are the post-remediation levels? And you can see a significant drop in the concentration. There's a thin, I think there's a thin blue line in the middle of the screen. That is the groundwater treatment standard, close to 70 micrograms per liter. The standard is for total chromium, and so when a regulator in New Jersey looks at it, they look at total chromium. And this really goes back to the question that Jill's asked before, that that way once you measure total chromium, it tells you how much is the hexchrome and the trichrome part, because you're measuring both hex and tri in it. So we can see there's 100% reduction at some location, 99% or 90% on some other locations. So once we learned during the pilot test that it's good, this ferroblack was used all over the site. Okay. This is just another picture showing you, what an extraction well and injection well looks like. Those wells doesn't need to be very large size wells. They could be 2-inch, 4-inch, 6-inch holes in the ground, and then we insert screens and the risers in them, and then you place the screens at the right location to extract water. Screens are basically just a filter for the groundwater. They can be made of plastic or metal. This figure shows you conceptually that what could happen, and this is just a conceptual diagram that you can see a very good industrial area. It could be much better than what it's looking on this figure, and people may have no clue what's in the groundwater underneath, and what they need to understand before remediation progress is where is the water table, in which direction it is flowing, what are the different layers of soil they can encounter. Soil itself can act as a reducing agent, because, for example, soil high in organic content, for example, peat or coal, they can have very high organics in them, and they will act as a filter as well as a chemical reductant. So it's very important to understand the soil heterogeneity before we progress into in-situ remediation. And this one shows you, how you can set up your extraction and injection well. You want to extract from less impacted area, and then you want to mix it with your reagents or the amendments that will do the actual reduction, and then you want to inject it back in at a location where your hexchrome concentrations are very high. So the understanding of the plume is the hexachromium mass dissolved in the groundwater. That understanding of the plume behavior and the understanding of the soil heterogeneity is the key in a successful and cost-effective remediation. You may not have enough budget to treat the whole site, but you want to cut the head of the snake. So understanding of the heterogeneity and the plume behavior is the key. This slide just shows a typical injection setup. It's a pump there, and you can decide, you can select or size the pump based on your needs of the site, based on how deep you want to inject, how much volume of water you want to move through, and you can size the pump based on that. And then there's a distribution skid that basically inject at least in this photo injects at, I think, 4 injection wells at the same time, and this skid could be downsized or upsized based on the site needs. It shows the injection well, a mixing tank, a generator for the power, and the overall hoses and the setup. One thing I want to point out, once these operations are started, there's a lot of physical hazard like trip, slips and falls hazard and pressure hazard. So if someone is doing that, he needs to have the right orientation about the hazards at the site, and needs to have proper training about how to inject. You can fracture the formation, which you never want to do if you inject at higher pressure. So it needs a person with the proper know-how to do these. But I wanted to show it to you. It looks fairly simple, and is a good photo to show what's an injection extraction process looks like. With that, I will go to questions. If you have any questions, and I know some of you might see the recording of this presentation. So here's my contact information. Please feel free to email me any questions or call me with your questions. It would be a pleasure to help you all. With that, I'll turn it to Lucy.
Okay, thank you very much, Sachin. As Sachin mentioned, does anybody have any questions?
Yes, Lucy, I have questions. So, can I ask?
Yes, of course.
Lucy?
Go ahead.
Yep.
Oh, okay. Thank you, Sachin, for a very informational information you shared with me. And this is a new thing for me, because I'm more familiar with lead and mercury contamination in Indonesia. So you mentioned in your first slide, chromate in paint. What is the function of chromate in paint? And you also mentioned that one method to prevent the inhalation of hexavalent chromium is to cover it with clean soil. Instead of clean soil, the same as lead, the #1 pathway to human is through inhalation. Can we also just pave it? We just put paving on top of the soil contaminated with hexavalent chromium?
Okay, so let me repeat the questions, Bodhi. So the first question is, what's the function of chromate salts in paint?
Yes.
And the second question is, if we have surface soils that are impacted, can we put paving, like asphalt paving, on it, right? Yes. Okay. So the first questions, the chromate salts in paints they provide longevity to the paint, more shelf life, and they also for cleaning solutions.
Okay.
And I mean, I'm not from a paint industry, but there are multiple applications of chromate salts. Once they are in the emulsified form, they provide the shine to it, basically, and color to it too. And of course, I think there can be many other functions. That would be a particular question to someone from a paint industry. I'm more focused on the remediation aspect of it. And the second question is, what can we do about the surface soils impacted with hexchrome? Of course, you can do asphalt paving on it, or you can put just clean soils on it. Asphalt paving would be costlier, but would be would have longer life to it, and you would have to maintain the asphalt. And the soils on it, you know, if you just put soils on it and then put some grass seeds on it that can naturally grow on it, it would be a cheaper choice. Both of them comes under an engineering control that needs to be maintained over time. The integrity of whether it's a soil cover or it's an asphalt cover needs to be maintained. What typically can happen in an asphalt cover, before you lay down your asphalt, the standard design calls for a drainage layer. And drainage layer is basically big rocks. So let's say you want to put your asphalt, you first have to lay down big rocks to that the size of those rocks could be 6 inches diameter to maybe sometime, you know, 10, 12 inches diameter. And you lay it down, that acts as a drainage layer. And on top of that, you have smaller rocks. And then on top of that, you have the asphalt coating, the actual coal tar that is coated on top. So when you put those big rocks, they, due to capillary action, the hexavalent chromium particles can enrich themselves within that drainage layer. And it may not show up at the top, but if you have cracks in the asphalt, which generally happen over time due to the temperature changes, you know, heat and cold stress, and that hexachrome particle, due to capillary action, can rise up and show up at the surface, and you can have a chromium blooms. So you would have to engineer your design of the asphalt in order to make sure that you have a capillary break layer before you lay down your asphalt. So one way to do it, just have large sized rocks. Don't have small sized rocks. The larger the size of a rock, lesser is the capillary rise. Capillary rise is nothing but rise of the water within small channels that are formed within small rocks. It's just a pressure difference that is created. Think of it as a chimney effect, that if you have a chimney, you know, your smoke goes from the inside of the house to the outside, kind of like that. So, and if you just put a soil cover, same thing, soil cover applies as well. You would have to engineer the size of the your soil particles so that you don't see a capillary rise in it. So you would choose soil which has a coarser grain to it. So you want to choose a very coarse sand. You don't want to choose a fine sand because that will have a very high capillary rise. And there's a standard equation to actually calculate how much capillary rise would happen based on the size of the soils. So those are the immediate thoughts that occur. And cost-wise, soil cover would be cheaper. What I would generally do, if you know, from cost standpoint, I would put the soil cover, but I would mix a reductant in it, so that it's even if it comes in contact with hexachrome particle, it can reduce it, and all those precipitates would settle down and itself become a barrier for the future propagation of the hexachrome upward.
I have one more question. What can we do with an area that has been remediated? I mean, it has been cleaned up from hexavalent chromium. Is it the same with an area that has been remediated from other, from heavy metals, for example, that it can be transformed into public parks, or we cannot grow something, a tree with consumable fruits? What can we do with an area that has been cleaned up from hexavalent chromium?
So when you say cleaned up, does it mean those soils were excavated out, or it were that the trivalent form of chromium is still there? How was it cleaned? That
clean up. But the chromium, hexavalent chromium is dangerous, but the other form, the how do you call it?
Trivalent.
This one is less dangerous, right?
Yeah.
So when it's transformed to this, then what can we do? So can I know both?
So what I was so Budi, what I was saying is that when you say a site has been cleaned, has the soils from that site has been excavated out, and it's clean soil that doesn't have either hexavalent chromium or trivalent chromium, or does that site has trivalent chromium left in it? What I'm
Still
trying to
trivalent. Oh, sorry. Yeah.
So yes, okay. So I think you said there's trivalent chromium still exists at the site, right? Okay. So I don't think you should put their tree with the consumable fruits on there. What could happen is there's a within a tree you can have rhizome degradation, and within the phytoremediation is another technology that is used to treat metals. But phytoremediation doesn't mean that you can put a plant there with the consumable fruits. Within the reaction that is happening within the tree, rhizome degradation can happen, and even if you consume trivalent chromium in higher dosages, it is not recommended. It's a micronutrient to the body. It is not supposed to be taken in higher dosage. I think the if you look up any vitamins bottle, I think their dosages in either I think picograms, like 20 picograms or so, or something in that neighborhood. So you don't want to consume fruits that has trichrome in it. You need very little of it, and I won't recommend. If there's trichrome that exists on that soil, don't put any consumables in there. You would still want to put some kind of clean soil over that surface soils that have trivalent chromium, because you can still have degradation of it, degradation by the natural ultraviolet rays. So I would still cover it with something, with maybe like 2 feet of clean soil, and over that I would put just grass, nothing else, because even if you put a plant on that, the roots can go through more than 2 feet deep very easily. I would just put grass on it and nothing else.
Thank you, Sachin.
Thanks.
This is Gilles here. Maybe my memory is not serving me well, but I seem to recall when I read Rich's book, that must have been a couple of years ago, that he was alluding to a particular site where the hexachromium was cleaned up, if I'm not mistaken, using worms. So they put some worms in the ground, and they actually fed those worms so that they would go and eat whatever was in the ground, including the chromium. And then when they stopped feeding them, the worms ended up at the surface and died, and they could then collect all those worms and get rid of them. Am I confusing that with another pollutant, or was that something that applies to hexachromium? And what do you think of this approach?
I have not come across that. Not to say that it can't happen. Typically, there is, I think in the Midwest somewhere, even in the United States, they found out that there was some a particular kind of bird that lived around a mining industry, that mining area, and they were able to eat, plants and the fruits around in that area that has high hexchrome in it, and in their intestines, they found a particular kind of bacteria that was able to treat hexchrome into trichrome. The problem with these kind of technologies that heavily relies on either worms or birds and biological kind of technologies, they can only be applied at a very low concentration. As soon as the concentrations are a little high, you get into a zone of biotoxicity, and you can't apply at that zone. So if the concentrations are low, this can be applied because body can only handle so much of abuse. And after that, it has to convert into a chemical reduction form. There's our livers and the livers of animals, they have only so much of capability to handle that toxicity. After that, it basically kills them. You know, those worms, they may, but I doubt they can function when your concentrations are, let's say, 20 milligrams per kilogram of soil or higher. It would be very hard to do that. That's why other technologies became more popular, because most of the time when you have concentrations that high, that becomes the concern. At lower concentrations, people are not so concerned about it, but at higher concentration, it becomes a big concern.
Okay, thank you very much.
Thanks.
Sachin, this is Conrad Meyer. First, thank you very much for this presentation. This has been very good and has answered a lot of questions that I have about the remediation process. I was wondering, and this is sort of a general question, but obviously whenever we're looking at cleanups, we are very focused on cost and getting as much done as we can for the dollars we invest. Could you maybe talk a little bit about how the various remediation techniques you've talked about vary in price, and how you think about price in trying to pick the right remediation process for a particular site?
That's a very good point, Conrad. Let me go back to that particular slide that has the alternatives. Yes, okay. So very good point. So one of the costliest option is the excavation. You don't want to excavate the soil. You don't want to pump all the groundwater or surface water to treat it. So the costs for excavation can range from $70 per cubic yard to, it could be as high as $120, $50 per cubic yard, based on the concentrations of the hexavalent chromium and other contaminants present in those soils. Slurry wall is also a very costly option. You need to have a very specialized kind of equipment to come out, and first it has to excavate a particular amount of soil and then mix those soils with very thick clays, and then try to inject it back. So you need a specialized equipment to do that. Very costly. Can range from similar $80 per cubic yard range. Another costly option would be soil mixing too. It's very costly. You need a specialized equipment to do that. Based on the depth of the soil, if it were to be, let's say, only shallow soils, mixing is easy. Any excavator generally available in all the countries can do that. But if the excavation depth or the mixing depth is, let's say, 20 feet below ground, then it becomes really hard. You need a special equipment to do that. There are special augers which are nothing but, think of it as a very big screwdriver, and have like thousands of horsepower in them. They can mix soils, and so it's very specialized equipment. Very costly option too. On the moderate to cheaper or cost-effective side would be injections, either chemical injections or biological injections. And you take groundwater, you can first extract it, or you can use any other water from tap, fire hydrant. You mix it with the water, your amendment, EVO, molasses, lactate, ZVI, and calcium polysulfide. You can mix any of those, and then you can inject it back into the ground. cost for this option can be as cheap as $30 per cubic yard to, and when I say dollar, I'm saying US dollar, but these costs can vary from country to country based on the cost of these liquid amendments that are available there. But generally in the United States would be somewhere from $30 per cubic yard to $50 per cubic yard. The choice, now we come to the choice. When do we choose one over the other? This is a very site-specific question. There are some general guidelines, but you would have to evaluate each site. It's a case-by-case basis. For example, you would want to understand how much is the groundwater velocity. If it is moving, let's say, 5 feet a day, and that is moderate groundwater velocity. 1 feet a day to half a feet a day is okay, to slow to average, but 5 feet a day is kind of fast. So you want to see that if you inject, would it just flow, dissolve away with the groundwater? You want to understand groundwater velocity. You want to understand soil heterogeneity. You want to understand how far the plume goes. You want to understand the natural geochemical conditions, and based on that, you would choose. And of course, the total depth of the impact, and the down gradient receptors that are getting affected. All those factors play into choosing a particular technology. Generally, if it is surface impacts, which are only 2, 3, 4, 5 feet deep, and you want to permanently get rid of it, just excavate it out. It's so shallow, and if it's a small area, it permanently takes care of the problem. If you can't excavate it, you would want to put an amendment on it. And when I say only shallow and 5 feet deep, I'm assuming there's no water table impacts. It's just only in the soils. If it's a water table impact, it'll change what you want to choose. So, again, going back to that, it's a case-by-case evaluation. Popular technologies, pump and treat, no doubt, but then, there are other instances where we don't need to do this. I hope I answered your question, Conrad.
No, that's very helpful. And obviously where it gets really complicated is where a cheaper methodology will have some impact, but not the same impact as a more expensive technology. And you have to decide between the two, whether it's better to treat 2 sites well, but not perfectly, or 1 site perfectly. And I guess that's a difficulty that you face in all cleanup situations.
That's true. That's true. And because our goal is to do remediation in the developing world, that could be very different for goals of remediation in the United States. Over here, we have to meet strict groundwater quality standards. But maybe in, let's say, in India or Indonesia, we don't have to meet those strict groundwater quality standards, but our immediate goal would be to mitigate the risk to the receptors, which is an immediate risk. So what methodology we choose to treat there, we can tweak it than what we would do over here. So if it's a surface soil impacts, it could be very easy soil cover. If it's groundwater impact, our first goal would be to make sure that nobody is at least using that water for potable uses. Nobody should drink that water. The awareness in the people to basically stay away from impacted area, I think, and then try to get funding for it, and then trying to design the most cost-effective alternative that could be taken up on case-by-case basis.
That was very helpful. Let me ask one other quick question, and then I'll back off. We obviously, in a lot of the situations we see, there is, and Budi talked about the lead situation with battery recycling, or mercury in the gold situation. where we're dealing with live situations where pollution is actually taking place. This may extend beyond the ambit of cleanup, but in the industries where we see hexavalent chrome being generated, do those streams continue, and are there things that we do to suggest changes in the processes of the people who are generating it to not generate more hexavalent chrome?
Right. That is a very good point. So, I mean, there is source point prevention. Typically, that is practiced in the United States. That means that prevent the release at the point of creation. So source point prevention. It's a program. It's very helpful. For example, let's say we have an electroplating industry where hexachrome is used, and once they are done with their operations, they discharge the effluent to a river, or they would be sending it to a treatment plant. Before they send it out, it's a normal regulation. They have to condition the effluent in order to make sure that it has minimal hexachrome discharge in it. Unfortunately, many times those standards or procedures are not followed in many countries, and the people just bypass completely the conditioning process, and they would discharge an effluent that is rich in hexavalent chromium or other contaminants, and that is truly a disaster. So it comes down to proper training, proper awareness to the people, and very important, the strict enforcement of standards by the regulators, implementation on the ground. So that's what it really comes down to. And the more we tell people about this, and more strictly it's enforced by the government, I think that's the key in preventing the hexachrome in the first place. All these industries, I'm sure they have standards, but they don't follow. Or they have been not following these for such a long time that they have complete ignorance to understand what can happen, what the disaster it is. Okay,
Thank you very much, all. If you have no more questions, we are going to end this session. Just a quick reminder, the recording of this presentation will be available online on the GAP website. And we definitely hope that you will be joining us for the next info session, which will take place on Thursday, April 20th at the same time. It will be on 6 crises, how toxic chemical contamination interacts with the other 5 global environmental problems the world faces. And it will be presented by our very own John Keith. The connection information will be the same as usual. Thank you all for your attention.